Metal powder and characterization. Poor quality of powder leads to defects in the end part, including pores, cracks, inclusions, residual stresses and suboptimal surface roughness. Therefore, powder characterization is important to ensure the quality of the powder required for powder bed fusion. Metal powder represents approximately 1/3 of the part cost. Typically 10 to 30% of the powder spread on the powder bed is converted into actual part. Powder needs to be recycled to produce cost-effective parts and justify the business case. However, recycled powder quality deteriorates over multiple heating and cooling cycles, and requires close monitoring and quality control over multiple uses. With repeated cycles, powder degrades in terms of interstitial contamination, and also sees change in particle size distribution. Note: certain regulated industries such as aerospace do specify only virgin powder for certain applications, which increases the part cost significantly. Thorough understanding of powder characteristics, specifications, powder production and the associated cost is necessary to consistently print good quality cost-effective parts. Additive manufacturing powder requirements are: good flowability, ability to spread powder evenly across the built platform. Good packing density and particle size distribution to reduce porosities. Must be compliant with alloy specification, chemical composition. Should be recycled for business case, quality control and regular monitoring is critical. Particle morphology, smooth regular shaped spherical particles. Powder must be consistent from batch to batch. Powder source must be traceable. Low on deleterious interstitials, contaminants and impurities. Powder manufacturing. Metal powder for powder bed fusion is mainly produced by the atomization process. Atomization employs the kinetic energy from a high-pressure liquid or gas to break apart a molten stream of metal into small droplets. These droplets solidify into spherical or ellipsoid shapes by the time they reach the bottom of the atomization chamber. Atomization is classified by the medium used to break the molten metal onto particles, such as by water, gas, or plasma. The cost and quality of the powder increase from water to gas to plasma atomization. The high-quality powder is referred to more spherical, less rough particles with a low level of contamination. Note: water atomization generally produces irregular and rough particles, due to the rapid quenching rates of the metal with water, whereas gas and plasma atomized powders produce highly spherical particles. These powders are preferred due to their good flowability and packing density. Atomization creates a wide powder particle size distribution between 5 to 500 micrometers. The powder is then segregated through sieving into narrower size distributions, as per the specification requirements. Compatibility of metal powder for powder bed fusion process is limited by metallurgical considerations, the atomization process used, and the rapid cooling rates. Weldability, absorption and reflectivity of the heat source by the powder are also important factors in powder bed fusion. Gas and plasma atomization has been mainly used to produce metal powders for powder bed fusion, such as alloys of titanium, aluminium, steel and nickel. There are more and more new material being evaluated and developed for powder bed fusion, which includes copper and magnesium base alloys, invar, tantalum, iron, niobium and other refractory metals. Powder characterization. Powder characterization comprises powder flow measurements, particle size distribution, packing density, morphology and chemical composition. The key characteristics of the powder are packing density and flowability. Powders that pack consistently produce high-density components, with fewer porosities and consistent quality. Powder flow is very important when feeding the powder from the hopper, and for creating consistent layers across the powder bed. This is directly affected by shape-poor morphology, packing density and particle size distribution. Additionally, powder needs to meet alloy specification, chemical composition, and have low deleterious interstitials and contaminants. Note: interstitial elements such as oxygen, nitrogen, carbon and sulfur can affect the melting and fusion dynamics of the powder, and increase porosities in the printed part. Powders must be free from foreign particle contamination, such as from other material batches at the powder production plant, or debris in processing, recycling equipment. Powder flowability. The ability to spread the powder evenly and smoothly across the bed, and form uniform layers with no air voids is dependent on the flowability characteristic, which is critical for powder bed fusion processes. Flowability is a function of friction between the particles, which is dependent upon the total surface area, and other surface properties such as smoothness and moisture. Rougher surfaces result in increased friction, while irregularly shaped particles are susceptible to mechanical interlocking. Both these effects decrease flowability of the powder. Note: spherical particles have lower resistance to flow than the irregularly shaped particles. Larger particle sizes have lower resistance to flow than smaller particles. Moisture content increases resistance to flow due to capillary forces between the particles. Flow meter. The powder flowability, that is flow rate of the powder, is measured using calibrated equipment, such as Hall flow meter and Gustafsson flow meter. Note: there are different ISO and ASTM standards, such as ISO 4490 and 13517, ASTM B213 and 964, available on testing methods of powder flowability. Particle size distribution. Particle size distribution indicates what particle sizes, in what proportion, are within a given powder sample. A general method of defining distribution is using three values, D10, D50 and D90 shown. D10 is the size where 10% of the sample population lies below the D10. For D50, 50% of the sample population lies below D50, and similarly D90 is a size where 90% lies below D90. Note: most metal powders fall in the range of 0.5 to 100 micrometers, and particle size directly affects the surface roughness of the printed parts. Smaller the particle size, smoother the resultant printed surface. Larger the particle size, the rougher the resultant surface. Analysis of metal powder particles has been carried out using different techniques, such as using microscope, sieves and laser diffraction. Laser diffraction is the most popular technique for measuring the particle size distribution of metal powders. Note: automated image analysis is an emerging technique that provides both particle size and shape information of metal powders. Packing density. Packing density is critical for powder bed fusion process, as it impacts the physical and mechanical properties of printed parts. A high packing density usually results in the production of high-quality parts, with low porosities and flaws. This can be achieved using a powder with relatively broad particle size distribution. In order to achieve the most efficient packing of the powder, different grades of the powder must be mixed together to minimize porosities. In the mixing process, the smaller particles get filled in between the interstices of the larger particles. This reduces the amount of voids, and consequently improving the packing of the powder and part quality. Note: maximum packing density is achieved with a distribution that includes both coarse and fine particles, where finer particles increase density by filling the interstices left by larger particles. Particle morphology. The morphology of a powder particle is characterized by the description of particle shape, such as spherical, angular, dendritic, nodular and irregular. The shape of the particle has significant effect overall on flow properties, powder bed packing density, and finally the build part density. Note: smooth, regular-shaped spherical particles flow more easily than those with a rough surface and irregular shape. Similarly, spherical particles tend to pack more efficiently than those that are irregular, giving rise to higher packing densities. Example morphology of 5 different stainless steel powders.